For this online lecture, I hope to introduce methods for monitoring convergence of MCMC chains. Let's see the method first and then an example. So one challenge in doing MCMC in practice is knowing when the chain has converged to its target distribution or the stationary distribution. Theoretically, we know that when the chain is ergodic, eventually as t goes to infinity, the stationary distribution converges to. However, in reality, nobody actually runs the algorithm for infinitely many iterations, and you have to stop somewhere. So monitoring convergence is important in determining how long should we set the burn-in cycle to be. These are the initial iterations that we toss away when we try to do posterior inference. If we run the chains for too long, then it's usually a waste of computational resources. MCMC algorithms for complex models in practice are usually computationally intensive, and running it for too long can take a lot of time and computational resources until we can reach conclusion. However, on the other side, you can't run the chain for too short either. So if you actually run the chain for too short and you didn't toss away sufficient number of burn-in iterations, what might happen is you're doing posterior inference before the chain has reached convergence to the posterior distribution. And that can lead to your samples not actually coming from the posterior distribution, and the parameter estimates and the inferences associated with them can be biased. So monitoring convergence is an important research problem, and there is a lot of ongoing research in statistics on this topic. For this course, we will discuss one of the most commonly used methods, known as the Gelman and Rubin R. So the Gelman-Rubin R hat, its formal name is the Gelman-Rubin estimated potential scale reduction. We denote the index by R hat, which is used for monitoring convergence of MCMC chains. In order to compute this statistic that in some degree reflects chain convergence, you actually have to run multiple chains with different initial values. Let's recall that earlier when we introduced the multiplication or the Gibbs algorithms, we usually only ran a single chain with an initial value. And we saw how that chain progresses over time. For the computing of the Gelman-Rubin R hat, which monitors convergence, what you need to do is to have multiple of those chains with over-dispersed initial values. Let's suppose that we have k separate chains, and each of them has a total of n iterations. Each of them has length n. The idea is that you want the k separate chains to have different initial values. And you want the initial values to be over-dispersed in the sense that they should be far away from each other. And let's denote the corresponding draws we have obtained from these chains across the n iterations by xij. So I is used to index the chain. We have a total of k chains, so I ranges from 1 to k. J is used to index the iteration number. So J can range from 1 to n, the total chain length. The idea is that we are going to compute some psi. So this Greek index over here, that is a summary statistic that estimates some parameter of the target distribution. For example, if your target distribution is the posterior distribution, you might choose your psi, the summary statistic computed from the samples, to be the posterior mean estimate. The essential idea is that psi is going to be a function of the random samples you have obtained from a chain. So let's use psi in to denote the summary statistic. Like the sample mean, you compute using the draws in the ith chain, ranging from the first iteration all the way up to the nth iteration. Intuitively, the idea is that although your k separate chains actually started from different places, eventually, if the chains have reached convergence, they should have reached the same places, right? The target distribution. So intuitively, if your n is sufficiently large for reaching convergence, we would expect the size that you compute using the first n samples from different chains with different starting values to be about the same, because they should have converged to these endpoints. So here is a really sloppy plot that I created. Here I just considered turning k equals to 2 separate chains with over the first starting value. But suppose that this middle part, so eventually where both of them get, is actually the stationary distribution. And you can see that in reference to the stationary distribution, starting points are quite far away, meaning over this first. So the black line over here represents the first chain, the chain plot for the first chain. Actually, the chain plot for the first chain. And the red line over here represents the chain plot for the second chain. Let's suppose that this vertical dashed line represents iteration n, where the x-axis is chain length, the iteration index. The idea of computing a psi I n, so in this case psi 1n or psi 2n, is that we are going to use all of these samples up to time n to compute that psi statistic. So you can see that over here, I actually index like psi 1 all the way up to psi 1n. The idea here is that you don't only have to compute it at n, you can actually compute the psi at any time point here. So let's say we compute it at the jth time point. Then we will have a psi 1j, which is computed using x11 all the way up to x1j. And you also have a psi 2j, which is computed using samples x21 all the way up to x2j, the jth iteration. So you can compute a bunch of these psis at different ending points in the chain, where each of them is the summary statistic, like the sample mean. You compute using all of the samples up to that iteration j. All right. So this psi is going to be useful when we compute the Gelman-Rubin R hat. The Gelman-Rubin method actually compares the between sequence variance to the within sequence variance of psi. So here is how we compute the between sequence variance. As the name suggests, is the variance of psi across sequences, right? Where here sequence stands for chains, right? We have a total of k chains. So what comes to this formula for between sequence variance is two things called psi dot bar and psi dot bar. If you have done ANOVA in the past, you might be familiar with this notation, where the psi dot bar is used to denote the average of the psi ij's within the ith chain. So the dot means like everything. It means that we're taking the average of every iteration in the ith chain, so a single chain. So you can see that it's actually just the sample mean across the n iterations of psi ij. The psi ij, again, is the summary statistic. It could be sample mean, it can be something else you're interested in that's computed using samples up to time j. Right? So if you have a total chain length of n, you can compute for each chain, the ith chain, a total of n of these psi ij's, or each of them using like samples up to time j. And then if you take the average of these guys, you get the psi I dot bar. So that's the average within the ith chain. Of course, you can also have a grand average across all of the iterations and all of the k chains. Right? So that's denoted by psi dot dot bar. So you can see that essentially is taking the average of the psi ij's, not only across the iterations in a single chain, but also across the k chains. So that's overall across the chains with different starting values, what is the average of this psi across the n iteration. And you can see that this B over here essentially looks at the average square deviation of the within chain mean of psi and the overall mean of psi across the chains. On the other hand, we can look at the within sequence variance of psi. So we have a total of k chains. Right? Within each of the chains, we can try to look at the sample variance of the SiJs within this chain. Let's denote that by Si squared. Essentially, you can see that it is the variance of Sij within the ith chain. It's the square deviation between the individual ones minus the mean within the ith chain averaged. So you will have a total of k of those. Say if you have 4 chains, like k equals to 4, then in this case you will have a total of 4 of these sample variance, right? 1 for each chain. Then you can get a pooled estimate of the within sample variance, which is essentially the average of the Si squares across the k chains. You just take the Si squares, take its average, and that gives you an estimate to the within sequence variance of that. All right. So when we compute the Gauss-Rubin R hat, the numerator R hat is going to be a variance estimate. It's actually a variance estimate for the upper bound of the variance, and it is actually given by a weighted sum of the B and the W. You can see that the weights actually depends on the sample size. So the idea is that if the chains of the random sample are the random samples from the target distribution, meaning that if your chains have converged and almost all of the samples are from the target distribution, then in this case, theoretically, you can actually have an unbiased estimate of the true variance of using R. However, let's think about what's going to happen to the W and the B if your chains have not yet mixed well by time n, meaning that they have not converged yet to the stationary distribution. Let's go back to this sloppy plot that I created. We have 2 chains, and you can see that at the very beginning, they're still pretty far from the stationary distribution where both of them tend to agree, right? So at the very beginning, you would expect that in this area, the size actually within a chain would be relatively small compared to what it is supposed to be. So the within chain variability is probably not large enough. The intuition is that it hasn't fully explored the target distribution yet. Hasn't gotten there. It might be moving too slowly, like we saw when we used a very small step when we did acceptance rejection, when we did metropolis. So if the chains have not yet converged and fully explored the target distribution, you would expect the within chain variability to be small. And that small is in reference to the between chain variability. Because we chose over the first initial values at the beginning of the chains, maybe they haven't started to converge yet. And in this chance, your B, which summarizes the between chain variability, tends to be large, right? It would tend to be larger than W, actually. And as a result, when you compute this var hat of psi we saw on the last page, you would expect this thing to be larger than W itself, right? You can see that W is actually n minus 1 divided by n times W plus 1 over n W. If you substitute the W here by B, which is larger than W, you would expect this var hat to be larger than W. So that's the intuition behind the Gauss-Rubin, which is essentially the ratio between this var hat and W, the within chain variability. The R hat is also called the estimated potential scale reduction for the following reasons. Essentially, the square root of R hat turns out to be an estimator, so it's actually an overestimator of the scale reduction factor, which is given by the square root of the var hat, the estimated variance, and the true variance of it. So this factor tells you the factor by which the standard error estimate of psi could be reduced by further extending the chain. So that's the potential part, potential scale reduction. So R hat can be interpreted as a convergence diagnostic, often as following the suggestions by R hat is much larger than 1, meaning that this R hat is much larger than W, then you would expect that if you run the chain for longer, it would either reduce the variance estimate of psi, or it's going to increase W, the within chain variability. It's pretty intuitive because you would think that if your R hat is much larger than 1, then probably the simulated sequences you have so far have not yet made a full tour of the target distribution. But if you run the chain longer, it might be able to take a fuller tour and explore the distribution more, which results in an increase in the within sequence variability. On the other hand, if you have a R hat that's close to 1, then we can conclude that each of the case sets of the unsimulated observations is close to the target distribution. In other words, we think the K chains intuitively with different starting values, they kind of converge to the same place. Usually in practice, people try to impose some sort of cutoff for R hat to determining whether they have run a sufficiently long chain to reach convergence to the stationary distribution. Common cutoffs include 1.2 or 1.1. Some people use more conservative cutoffs like 1.05. So in that case, you will be more careful in concluding that you have converged. You will look at your observed R hat value at a particular number of iterations. You see, is it, say, larger than 1.2? If not, then you can say, based on the cutoff of 1.2, I can conclude the chains have converged. If it's greater than 1.2, you might say, okay, I need to run the chains longer, or there's something wrong that's going on with my algorithm. All right. So that's a conceptual introduction to R hat. What I want to do now is try to do a simple example. Let's consider that we're going to construct a MH sampler where the stationary or the target distribution is the standard normal. What we're going to do is to run several different chains and try to see how long do we need to run the chains for them to reach convergence. So we're going to compute R hat. So this is a very toy example where your target distribution is something that's quite simple, the standard normal distribution. It's straightforward to sample directly from standard normal, but just for the sake of illustrating this problem, let's assume that we are going to take a detour and construct a MH sampler, a Markov chain whose stationary distribution is normal 0, 1. So let's recall that for a MH algorithm, we need to specify what is the initial value, what is the transition kernel. For the transition kernel, we need to specify what is our proposal distribution for drawing the next proposal sample given the current X. Right? We also need to specify the number of iterations. For this example, let's suppose that we are going to run the MH algorithm where our proposal distribution is y given xt follows a normal distribution with mean xt and some variance sigma squared. Earlier we said in general it can be some sort of summary statistic that's computed using the samples, right? In this case, let's just use the sample mean. So psi is going to be the sample mean computed using the growth up to time driven or time. To run this, we are going to first write a function for computing Gellman-Rubin R hat. The idea of this function is that it's going to be a generic function where it takes a data set of the size, so across the chain, across the iterations, and it's going to compute the W and the B we saw earlier and use those to compute the R hat statistic. This is actually a generic function, meaning that if you have the size from some other MH algorithm with some different posterior or target distribution, in that case, you can directly take this function for computing R hat, and this should be still directly usable. Okay, so before we see the function, let me explain the input a little bit. So we mentioned that the R hat is computed using the psi ij's. Right? Psi ij's, each of them is the summary statistic. For example, the sample mean computed using the draws up to time j for the ith chain. So the input of this matrix is going to have a total of k rows representing the k chains with different starting values, and it's going to have a total of n columns, where n is your total chain length. And each of the column, which we denote by the jth column, represents the psi ij for up to the jth iteration, using samples computed up to the computed using samples up to the jth iteration. All right. So here's the function. Input is this psi matrix, k rows. Each row, the ith row is for the ith chain, and n columns. Right? And each column, the jth column, corresponds to the jth iterations psi. So let's first make sure that it is a matrix by doing as matrix. And then n is the number of columns. That's our number of iterations in total. And k is our number of rows, which is how many chains that we're doing. Okay, so let's recall that in order to compute the r hat, we need to compute the within chain average, the psi dot bar. We also need the grand average, which is the psi dot bar. Let's get the psi dot bar first. Essentially, it's just going to be the row means of this psi matrix, because each row is a chain, right? If we take the average of that row, then we get the psi dot bar. We should have a total of k of those. It's called psi means. And then we can use this to compute the between chain variance. And essentially, the b we saw earlier will be given by n times the variance of the psi means of length k. We also need the within sequence variances. Right? Let's recall that we need to first get the si squared, which is essentially what is the variance of the size within each row. That can be obtained by doing apply to this psi matrix, and each row is margin x1, a variance function. Right? This should return you a total of k of those si squares. And if you take the average of them, that gives us the w, right? The pooled within sequence variance estimate. Then we can plug in the w and the b into the earlier formula for the variance hat. And the r hat statistic is going to be given by this bar hat divided by w. And that's what we're going to return in this function. So as a summary, this function takes a matrix of those size across chains and across iterations as input, and it returns a single number, which is the r hat computed using these guys. All right. Let's also create a function for the MH algorithm. The essential idea is that it takes a bunch of arguments, like what is the potential standard deviation for the random walk sampler, what is going to be the variance that we will walk from the current xp. N is the total chain length, and x1 is the initial value for that chain. This function is going to return you x, which is a vector of length n, which contains the x rows of the MH algorithm across the system. So let's begin by creating a placeholder of a bunch of zeros that will be used for storing the draw. We know that the initial value for this chain should be equal to x1, our argument of this function. So let's set the first entry to be 1. This uniform vector of length n is used in the acceptance rejection step of the sample. Now we iterate for each I from 2 to n. For each of these iterations, let's set xt to be the current place of this x chain. So that's given by the I-1 entry of x. Now we generate the proposal draw, which is from a normal distribution with mean of xt and standard deviation of sigma. In reality, you might tune the sigma to try to make the chain converge faster. But here, let's try to do an illustration of the convergence diagnosis. So I'm not going to play with the sigma value, and we'll just set it to an arbitrary number later on. So now we have a proposal draw y from this normal distribution of xt and standard deviation sigma. Next step is to use the proposal draw y and the current xt to compute that acceptance probability given by that ratio that depends on the proposal density and the target density. Our target density is normal 0, 1 density. That's given by the norm of either y or xt with mean of 0 and standard deviation 1. Our proposal density is also a normal density, where the mean is actually either y or xt, and the standard deviation is sigma. Right? So you compute the R1 and R2, which are essentially the numerator and denominator. Taking their ratio gives you the acceptance probability. You compare that uniform random number you generated to this acceptance probability. If it's less than that, we accept the draw and set the next x to be equal to y. Otherwise, we reject the draw and set the next draw of x to be where it is at right now, right? Which is x. In the end, we return the chain of x. So this normal chain function is helpful for generating a single chain with some specified transition kernel, which is essentially the proposal standard deviation, chain length, and initial value. Because we're going to monitor convergence, we are actually going to generate multiple of these chains that share the same chain length, the same transition kernel, meaning that the same sigma we used in the proposal density, but with different dispersed starting values. In general, if you ask the question of how many chains you should run for doing the R hats, I'll say the minimum is 2. You can't compute this thing with just one chain. The minimum you need to compute R hat is actually k equals to 2. So you need 2 separate chains, like we saw in the plot earlier. However, I would recommend you to use maybe more chains in general. So I would suggest maybe running 3 or 4 chains, unless it's extremely slow and difficult for you to run more than 2, because it has been shown in some studies that if you only run 2 chains, your R hat estimate can actually be unstable sometimes and give you wrong conclusions. So for this example, let's follow this advice and generate k equals to 4 separate chains with different starting values. We want these starting values to be over dispersed compared to the target distribution. And 0, 0, 1. That the 4 different x zeros we used are truly over dispersed. So the minimum is -10 and the maximum is 10. Let's just set the proposal standard deviation to be sigma equals to 0.5 across the 4 chains. The total number of iterations or chain length, let's set it to be 15,000 for chains. And let's suppose that when later on we plot the chains and do inference, we will toss away the first 1,000 and turn it B. Let's first now create a matrix X, which is a placeholder for storing our draw, which are our x's, that should at some point converge to the stationary standard normal distribution. So the x's will be used for storing the draws across the chains and across the iterations. It has k rows and n columns. Let's set the initial values to be -10, -5, 5, and 10. We can actually apply the earlier normal chain function we have created to fill in each row with each chain samples for this X matrix. Right? Let's set the ith row of this X matrix containing the draws to be the output of the normal chain function we just created, where the proposal standard deviation is 0.5. Chain length is 15,000, and the initial value is actually going to be different for different cases. So depending on whether it's the first chain or the 4th chain, then you have the initial value of say, -10 versus 10 instead. If you look at the dimension of X, I have 4 rows, 4 chains, and 15,000 columns, or 15,000 iterations per chain. Okay. I'll quickly try to run this part inside R. So that's the Gelman-Rubin function. Here's the normal chain function. And once we have these 2 functions, I do want to show you what the x's look like. And you can see that I actually took a little while, right? although it was actually a very simple target distribution. So we saw that the dimension of X, it has 4 rows and 15,000 columns. What you can also see is that, let's say if we look at X, like maybe all the rows, but the first 5 columns, you can see that the first column are our initial values for the 4 chains. Second column is actually the image draws in the second iteration across the 4 chains. You can see that in chain 3 is actually rejected, so it stayed at 5, right? So essentially across the 15,000 columns is going to contain the X samples you got within that chain. All right, so the X's or the samples are going to be helpful when we compute the psi, right, which we need to compute the R hat. The psi in this case, the psi j's, is actually the mean of the X's in the ith chain from time 1 to time j. The essential idea is, let's think about how you compute this thing. We have the X's now organized by rows, by chains, and by iterations. To compute star ij, essentially what you need to do is to sum up within the ith row the X's from the first column all the way up to jth column, and then you divide it by j. So let's try to do that and compute the psi j's. Here we're going to use vectorized operations where we actually will, instead of writing a for loop, we're going to generate this psi matrix by doing matrix operations. I'm going to start from creating a matrix called sums. You can see that it's obtained by applying to the X matrix of samples to each row the cum-sum, the cumulative sum function. Right? What it's going to do is to apply each row the cumulative sum, where sums up for the sums matrix, the first column, first entry will be within the ith chain, the xi, x1. And then the second entry is going to be x1 plus x2. And the third is going to be x1 plus x2 plus x3. If you actually do it this way and you look at the dimensions of sums, I found it funny that it's called dim sums here. It will have actually a total of 15,000 rows and 4 columns. Let's take a look at this sums. So like I said, the sums is actually going to have a total of 15,000, and it kind of transposes the X matrix. If we look at the head of sums, you will notice that it's actually doing cumulative sums within each chain. Let's call that the initial values. So this row, the initial values don't change. But if you look at j equals to 2, so the second time point, you can see that it's actually the sum within the chain of the first sample x and the second sample x, etc. So that's the cumulative sum, but instead what we want is some sort of cumulative mean. The essential idea is that we want to divide by each sum, which iteration it is. That's the number of iterations we're summing over, and that will give us the size, which are the sample means up to the jth iteration. So what we're going to do is to do our psi is going to be the sums matrix divided by the vector 1 through n, so 1 through 15,000. When you do this, it's actually going to do entry-wise division. And what's going to happen is that this is going to be divided by 1. This thing is going to be divided by 2. This thing is going to be divided by 3, etc. And the 15,000 row of the sums matrix is going to be divided by n, 15,000. And that actually gives us the sample means that we divide. So let's try to do this. You can see that the psi matrix is essentially is the average of the draws up to time j for each time point between 1 to 15,000. Okay, that's a little bit different from the input format we want. Now we have a total of 4 columns and 15,000 rows, but instead what we want is to import as 4 rows for a chain and 15,000 columns. Right? So let's say that our psi is the transpose of this side. So essentially, we're flipping the rows and columns so that matches with the input of the Gell-Mann-Rubin function we just created. Now we have the psi matrix containing the means, cumulative means for each of the chains. We can now compute the Gell-Mann-Rubin statistic by applying the Gell-Mann-Rubin function we just created. Okay, because I highly suspect that if I run it inside R, it's going to give me a slightly different value from 1.14 since my speed is different. So let's just try to look at the slides. If you say Gell-Mann-Rubin applied to the size in this case, for this particular set of a total of 15,000 iterations with these initial values, we got a Gell-Mann-Rubin R hat of 1.15 approximately. If you use a cutoff of 1.2, which is very common in the literature, then you would conclude that your observed R hat of 1.148 is actually less than the cutoff of 1.2. So it's actually closer to 1. And that suggests convergence. That's good. Okay. What I'm going to do next is to generate a set of plots. Let's start with something that we have already done in the past, which is the chain plots. In this case, we have a total of 4 chains with different starting values for this MH sampler that should converge to the stationary distribution of normal 0, 1. So let's try to toss away the first 1,000 iterations that burn in, and using the remaining 40,000 iterations, generate the chain plot for each of the chains. And let's see what they look like. Here's the code for generating the plots. You see that essentially I'm going to create 4 plots, each for a chain. For each of the chains I'm going to do is to plot, instead of the x's, the psi values, so the means computed using the samples of that I've chain. From the b plus 1th iteration to the nth iteration. So I'm not plotting the first 1,000 sites, but just the 1,001st to 15,000. So these are the chain plots for sure. Let's recall that chain 1 has a starting value of -10. Chain 2 has a starting value of -5, and the other 2 has like a +5 and +10. You can clearly see that at the beginning, even at iteration 1000, some of these chains, you can see that it's still pretty far from the stationary distribution, which could be centered around 0. So for example, the first chain where we started somewhere truly negative, by time 1000, the psi is actually still pretty far from what it should be. It's 0. Similarly for the second chain, the other 2, because the initial values were so large, by time 1000, they're actually still pretty far away from 0 as well. Right? They're more positive. However, hopefully at the end, when we concluded that they reach convergence, you can see that each of the chain's size, they're still fluctuating, but closer to what we think they should be fluctuating around. Okay, so I also want to illustrate to you a very common practice when you monitor convergence, which is making convergence plots. The idea is that very often people want to generate a convergence plot which describes, as you increase the chain length, how does the R hat value computed up to this point in the chain length change. Intuitively, you would think that if your chain length is short, your R hat is large. Intuitively, it hasn't reached convergence yet. But as you increase your chain length, your R hat would get closer and closer to 1, and eventually pass that threshold of the cutoff for convergence to design. So that's called a chain plot. Essentially, it looks at different possible chain lengths and how your R hat changes as it decreases over time. In order to obtain that, the idea is that instead of using a fixed total chain length n, you are going to play with different choices of chain length. Very commonly, you would incrementally increase your chain length, maybe at intervals of, say, a chain length of 100, 200, all the way up to 15,000. Right? Every time you increase the chain length by another 100, and using the size computed up to that total chain length, you compute R hat, record that, and then you plot that in a line plot. So here's the code for creating chain lengths from scratch. So this is one version of it. I know that some packages actually use different versions of this thing, but the essential idea is about the same. So let's create a placeholder of length n for our hat. Essentially, we are going to play with possible possible chain lengths of ranging between number of burn-in iterations all the way up to n. And we're going to record the computed R hat values using that particular chain length. So for each number of iterations between b plus 1, b is burn in, all the way up to total maximum chain length, we are going to compute R hat, not using all of these size, but only using the size that we get from iteration 1 up to that j, the jth iteration between 1001 to 15,000. So you can see that here, the only difference is that we are computing Gelman-Rubin, where the input is a subset of the sign matrix. We're not using the total of 15,000 columns, but we're just looking at the first j columns. And that tells you that iteration j was the R hat. So that's stored inside this R hat vector. You can then create a line plot of this R, where the x-axis is going to be the number of iterations, which in this case will range from b plus 1 through n. Y-axis is at this iteration number, what was the computed R hat you had. Usually what I also do is I try to impose a vertical line, a horizontal line for the cutoff we use for concluding convergence. So in this case, let's say we use a cutoff of 1.2. Whenever the R hat reaches below 1.2, we say, okay, we converge. We can start tossing away these and use the subsequent ones as post burn-in iteration. So that's what the AV line here does. Like h equals 1.2 means I want a horizontal line at 1.2. So this is the resulting chain plot. Essentially, what tells you at different number of iterations, what does the R hat look like? And you can actually conclude here that at approximately 8,000 iterations, our chain reached convergence. So using this, you can provide people with advice. Like whenever you run my algorithm, then you can actually use a burn-in of size 8,000. And usually if you use the post-burn-in iterations after 8,000 for your inferences, you can actually be pretty confident that you are drawing inferences using converged samples or using the posterior distribution samples. Okay, so essentially for this lecture, we tried to compute R hat and make the convergence plot from scratch. An alternative to it is to use the CODA package inside R, which is very commonly used when you want to compute convergence diagnostics or generate convergence plots. The CODA package actually does a little bit more compared to what we saw in this lecture. For example, it can give you confidence intervals for R hat, and it can also give you multivariate versions of R hat. We're not going to talk about how to call the package here, but in the next homework assignment, you will actually have an example that involves using CODA.